Thank you. So this is the title, is the plan. So I want to give a survey of the history of alternating sign matrices. Certainly it will be from my point of view, and therefore you may not agree on some things. And I may also forget some things, so I apologize in advance for anything that I forget. But so one thing that I won't forget is to define alternating sign matrices. When you put this away, it's not important for this page, but later on. I think one can put it on the side or so. Hmm? Click on one. Okay. Okay. Alternating sign matrix is a square matrix. The entries are zeros, ones, and minus ones. And when you read along a row or along a column and ignore the zeros, then you read 1, minus 1, 1, minus 1, 1, minus 1, and so on. And it starts with a 1 and it ends with a 1. And I'll show you here one example of such an alternating sign matrix. Right, at this point, I should also say that many of you won't see anything new in my presentation, but given the title, that's more or less on purpose, but I think I have a few things that you have not seen before. Anyhow, so the title here says the birth, but now I can't move the... No, it doesn't. Where's it? No, it's strange. Something is wrong. No, something is wrong. It should work with the arrows. It doesn't do anything. The title page does not come when I scroll with this. It should be right. Yeah. I did that before. So for those who have not seen alternating sign matrices before, you might ask the question, why alternating sign matrices? And the reason is written down in this paper by David Robbins and Howard Ramsey. So the date is not the right date when they actually did this work. So what they looked at was a generalization of the determinant, which they called the lambda determinant, and the background is a formula for the determinant, which for some is Stotchen's condensation formula, for others it's a formula due to Jacobi. Special cases have been found before by other people. Anyhow, so what the formula says is when you take the determinant of M and multiply it by the determinant of the submatrix where you delete the first row, first column, last row, last column, then you can express it as an expression in terms of other minors of the same matrix. Namely, in the first one, you have submatrix where you delete first row, first column. Here you delete last row, last column. And you subtract the product where you do this in a mixed version. Last row, first column, first row, last column. And this is called Dodgson condensation because Dodgson proposed an algorithm to compute the determinant by dividing this minor. And then the determinant of M is expressed in minus of the matrix. And therefore you can recursively compute the matrix, compute the determinant of a matrix by this formula, hoping that the denominators will not be zero. So it's the same thing again. And now Robbins and Ramsey said to themselves, let's generalize this. So instead of having -1 here in the formula, put lambda. And then use this to define what they call the lambda determinant, the generalization of the determinant. All right. So from the outset, what you will get is a rational function in lambda. Because, sorry, you will get a rational function in lambda and the matrix entries. But the surprise is, which they observed, that you can express the lambda determinant in terms of a formula that is similar to the standard formula for the determinant that we know as a sum over permutations minus the permutation product of the matrix entry. The difference now is that the sum is over alternating sign matrices. You take the product of matrix entries raised to the corresponding element in the alternating sign matrix. And then you have two more terms. You have the power of lambda, you have the power of 1 plus lambda. And the power of 1 plus lambda is the number of -1s in the matrix. And it's the power of lambda involves the inversion statistics of an alternating sign matrix, which is the sum of products of entries of the matrix, which are located anti-diagonally. If you think for a moment, then you realize if I have a permutation matrix, then this will be the inversion index of the permutation, and so we call inversion of an alternating sign matrix. So it is interesting to note that this is the first instance that has appeared of what was later called by Fomin and Selevinsky the Laurent phenomenon. Namely that you define a sequence by an algebraic recurrence and you expect to get a rational function, but by some miracle you get Laurent polynomials. Right, so here are the first few matrices. There's one by one matrix. There are two by two matrices. There are now 7 3 by 3 matrices. So the permutation matrices are always alternating sign matrices. This is quite obvious. And in the case of 3 by 3 matrices, we have the 6 permutation matrices, and then this additional matrix, which contains a -1. And then if you look at the numbers, and this is what Robbins and Ramsey, and then from a certain point on, also Will Mills, the number theorists, joined. These are the first few alternating sign matrix numbers. And by not only looking at these numbers, but also on a refined enumeration, Niels, Robbins, and Ramsey were able to figure out a formula for these numbers, but of course only conjectural. So there exists an article of David Robbins in the American Mathematical Monthly where he tells his involvement in the story. And what he tells is that they were very excited to find this formula, and now they tried to prove it for several months, but they failed. And then they had the idea to contact Richard Stanley. So they asked Richard Stanley whether he has seen this problem, these numbers. And Richard Stanley replied, I can't prove this conjecture, but I have seen these numbers before, namely as numbers of descending plane partitions. And indeed, these descending plane partitions have been defined and enumerated by George Andrews just a bit before. So what is a descending plane partition? You should not memorize this definition. I just show you the original definition of George Andrews, which is in terms of arrays of numbers, which satisfy certain complicated conditions. So along the entries along rows are weakly decreasing, the entries along columns are strictly decreasing. Then this shape must have this form. And this is here this condition. The first entry in each row does not exceed the number of entries in the row. Okay. Here's another definition. There's a bijection with rhombus tilings of a hexagon with side length n plus 1, n minus 1, n plus 1, n minus 1, n plus 1, n minus 1, where you remove a triangle of size 2 from the center. And when I say rhombus tilings, then I mean that you cover this hexagon minus triangle completely by unit rhombi without overlap and without any missing things. So here's an example. And in addition, these rhombus tilings must be cyclically symmetric. Namely, if you rotate the picture by 120 degrees, you get the same thing. This is also very weird, but this is easier to understand. Then you still may have the question, why descending plane partitions? The descending plane partitions. All right, so here's the theorem. George Andrews had proved that the number of order n descending plane partitions is given by this number that Mills, Robbins, and Ramsey had found, apparently to count alternating sign matrices. So why descending plane partitions? So Andrews was actually trying to prove a conjecture on the number and actually on a generating function, a Q analog of the number of cyclically symmetric plane partitions. And I will say more about this not so long from now. And while doing this, he translated these cyclically symmetric plane partitions in areas of numbers like we have seen for the descending plane partitions. And he saw a way to generalize this and to introduce a parameter. Yes. Yeah. Right. He saw a way to introduce a parameter. Something these things come five. Okay, there's something missing. Anyhow, so you saw a way to introduce a parameter. And then he enumerated these more general objects, which he was able to do. And then he also looked, when can we have two analogs? So for the cyclically symmetric plane partitions, yes. And there was only one more instance of the parameter where a Q analog seemed to exist. And these are the descending plane partitions. Okay, so then, and this is also what Robbins writes in this paper in American Mathematics of Monthly. Okay, so if these alternating sign matrices have something to do apparently with plane partitions, then we should learn plane partitions. So here is what plane partitions are. This is not the original definition. Plane partitions were introduced into mathematics by Percy Alexander McMahon around 1900. But this, if you like, is the modern view of plane partitions. The plane partition in an A by B by C box is a rhombus tile length of a hexagon with side lengths ABC, ABC. So in this case, all side lengths are the same, but it could be that they are not the same, but what has to be the case is that opposite sides have the same length. And again, a rhombus tiling is a tiling by a unit rhombi, and you have to tile everything without overlap and without missing it. So plane partitions can have several symmetries. And in fact, namely the symmetries of the hexagon. So for example, we could have this reflective symmetry. This one has this reflective symmetry. These are called symmetric plane partitions. Already McMahon considered them and had a conjecture about the enumeration. Then we can have the horizontal symmetry axis. This one is also symmetric with the horizontal symmetry axis. Then this is called transpose complementary plane partitions. And then you can also rotate by 120 degrees, then it's cyclically symmetric, and so on. And if you combine all possible symmetries, then it turns out there are 10 symmetry classes of plane partitions. And Richard Stanley proposed to enumerate all of those. And the very surprising thing is that it turned out that for all 10 symmetry classes, there exist compact, nice product formulas for the number of these plane partitions. And in 4 cases, also two analogs, which I will not present. Okay, so let me quickly go to the symmetry classes of plane partitions. So here's the first one. The number of plane partitions contained in an A by B by C box without any further restrictions is given by this nice product formula. And this is something that McMahon already proved around 1900. So he himself introduced symmetric plane partitions, those which are invariant under a vertical reflection. And McMahon had a conjectured formula that George Andrews had already proved at the time that I'm currently considering. Then there are cyclically symmetric plane partitions, those which are invariant under 120 degrees rotation. And George Andrews had just proved an enumeration formula, and as I said, actually a more general formula for a parametric class of combinatorial objects. And for this formula, there's also a Q analog where each plane partition is weighted by Q to the volume of the plane partition. Totally symmetric plane partitions. These are the ones which are symmetric, so vertically symmetric and invariant under 120-degree rotation. And here, McDonald and Robbins conjectured a nice product formula, but at the time, it was not proved. And for this one, also a Q analog exists. In this case, you have to do an orbit count, but I will not go into it. So the next case is self-complementary plane partitions. These are the ones which are invariant under a rotation by 180 degrees. And again, there are very nice formulas. Here it's expressed in terms of the number of unrestricted plane partitions. At the time, this was again a conjecture. Then transpose complementary plane partitions. These are the ones which are horizontally symmetric. Again, a nice formula seemed to exist, but it was not proved at the time. Next, symmetric self-complementary. Again, a very nice formula. Here expressed again in terms of unrestricted plane partitions, not proved. Then cyclically symmetric transpose complementary plane partitions. Again, a nice formula, not proved. Ninth class, cyclically symmetric, self-complementary plane partitions, nice formula, not proved. And then conjecture by Andrews and Robbins on the number of plane partitions with all symmetries. Okay, very nice. And here we see again our alternating sign matrix numbers. Not proved at the time. Okay. So Mills, Robbins, Ramsey said to themselves, so if there are these symmetry classes of plane partitions, we should look at symmetry classes of alternating sign matrices. This is what they did. So this conjecture we already know, the number of n by n alternating sign matrices is given by this famous product formula. At the time, a conjecture. But then you could have alternating sign matrices which have the symmetries of the square. In this case, it's not the hexagon, but it's the symmetries of the square. And in this case, it turns out that there are 8 symmetry classes of alternating sign matrix conjectures. So, for example, those which have a diagonal symmetry. But if you look at the numbers, then you realize that there can't be such a nice product form. Okay, in this case, vertical symmetry. So there's a vertical symmetry axis. Then you can convince yourself for even size, this is impossible, but for odd size, there's again a nice formula. So it's written in a recursive way. Class 4, half turn symmetric, so you do a 90 degrees rotation. And then again, there are very nice formulas here given in a recursive way. Then next, diagonally and anti-diagonal symmetric, so diagonally symmetric, anti-diagonally symmetric. Again, there's a nice product formula for even for odd size, sorry. But for even size, the numbers are not nice. So for even size, such a formula will not exist. Then vertically and horizontally symmetric alternating sign matrices. For the odd size, there are nice formulas, given again recursively here, but for even size, there cannot be a nice product formula. And finally, all symmetries, where the numbers are again not nice, there's no nice product formula. Okay, so what was the progress on these? These were the problems that Richard Stanley primarily advocated and made popular by own articles and talks. So what was the progress? So slowly the plane partition conjectures got proof, and interestingly, so this Robbins-Ramsey coming from alternating sign matrices went into plane partitions, learned all the techniques, and proved two of the conjectures, one of which is the Q analog of the cyclically symmetric plane partitions, and actually also the Q analog of the descending plane partitions. So here I have more text on George Andrews' attempt to prove the cyclically symmetric plane partition conjecture. He introduced objects that had a parameter. He was able to enumerate them, but for the Q analogs, he was not able to. And the Q analogs only exist when this parameter mu is 0 or 2. For 0, this is cyclically symmetric plane partitions. For 2, these are the, as Andrews called them, descending plane partitions. As I said, Niels Robbins-Ramsey proved both Q analogs. Then, apparently, since Richard Stanley proposed the problems, his students had to prove the conjectures. So Bob Proctor jumped on this, and he proved the formula for class 7. He proved the formula for class 6. And Stanley himself proved the formula for class 5. Niels Robbins-Ramsey again proved the formulas for class 8. Then Greg Kuperberg, so there's again a few years, then Greg Kuperberg proved the formula for class 9, and Andrews proved the formula for class 10. Sorry, for class 4. No, 9, no, he proved the formula for class 10. The only thing that was open, right, was class 4. Stambridge proved the enumeration, but not the Q analog. The Q analog one had to wait until 2011 when Pucham Cowers and Zellweger proved it. Right. So you will have observed that so far I talked about plane partitions, what about the alternating sign matrices? The truth is that for many, many years, nobody knew even how to attack the problem. Nobody had any approach to it. This changed in 1992, 1993. Then some people received an email by Doron Zellweger, in which he put a certain constant term identity, and he told us that if one could prove this constant term identity, then a very famous problem will be solved. And I have forgotten what exactly he offered, whether one should write a note on the constant term, it would be acknowledged in his paper. Whatever. So a few months later, in 1993, Zellweger told us now he has proved the identity himself, and he distributed a preprint, of which we see the first page here, proof of the alternating sign matrix conjecture. And there follows an introduction of one page of, so how should I phrase this, philosophical remarks on things that don't have much to do with the alternating sign matrix conjecture. But on the second page, we realize that he starts to talk about alternating sign matrix conjectures. The paragraph above is still general philosophy. And here's the famous formula. We come to the third page, which is quite interesting because of the acknowledgement. I wish to thank two anonymous reviewers of my last NSF proposal, who, in their elsewhere favorable reports, expressed doubts that I'm able to solve problem number 11, which was the alternating sign matrix conjecture. One of the reviewers said, in fact, that it's like the Riemann hypothesis in the field. And so Orwell said, no doubt, their doubts combined with my own contrary and quarrelsome nature contributed to the success of this project. Yeah, more interesting thing on this page. Maybe they how to read the paper. Well, you should read the proof as it has been found. So first you have to read it for k equals 2. So this is the dimension of the alternating sign matrix. Then you should read it again, but with k equals 3. Then again, but with k equals 4. Then again with k equals 5. And then in general. And there is further advice for the journal editor. So the journal editor should appoint a main referee and several sub-referees. And okay, so we understand. And there's one more interesting thing. So this is the last page. So if we go down a bit, 23 pages. So very nice, compact. Then at some point, some people, I was among them, received a very strange email from Andrew Ozichko, who reported that he was editor, I think, of the Journal of the American Mathematical Society, and he was handling a paper which, if okay, correct, was a great achievement, but the problem is that the referee finds gaps. Then the paper goes back to the author corrects something, submits the paper again, and the referee finds new gaps. And then the paper goes back again, and it's again something done, resubmission, and again, new gaps. And apparently this, this happened for some while. So I suppose that at some point, either the editor or the referee lost patience and probably told Doran Seilberger, so when you submit the next time, or when we reject it. Anyhow, the message certainly was, here, Doran, you have to do something with that. So either read the proof carefully, check the proof carefully. If you are not able to do that, give it to some student, but please do something. And so Zeilberger did something, and actually he followed the advice to the editor that we have seen. First, apparently, for the first time, he carefully read his proof and designed the paper completely hierarchical. So the main theorem is lemma 1, and which is based on sublemma 1.1 and sublemma 1.2 and sublemma 1.3, which in their turn are based on sublemma 1.1.1 and so on. And then he sent his new paper to about 80 referees. And each of them was assigned 2 to 3 pages of the paper, which had to be checked under the assumption that everything which in this proof hierarchy is further up is correct. So this was done. So I had my 3 pages, and indeed in my 3 pages there was something which was not completely okay, but it was easy to fix. And so finally, after everything came back, the paper was published, not in the Journal of American Mathematical Society, but in the Electronic Journal of Mathematics, in a special issue for Dominique Fouattard. So now the title looks exactly the same, but then there's the first change, because it says checked by, and then there is this main referee. This is David Brisson, who surveyed everything, and then here are the 80 checkers. So as I said, here's the main theorem is lemma 1, which is based on subnormal 1.1 and so on, and then this goes up to the 6, if I count right. And again, let's look at the last mathematical page. So after this last mathematical page, there follow 10 pages of short descriptions of the checkers. And also it is told who checked what. So let's scroll down. 73. Quite some change. So how did he prove it? So Zeilberger's method was to use constant term identities. And for him, this was quite natural, because before that, he had looked at and also worked at the McDonald constant term identity conjectures, and with some success. And then at some point he had the idea, maybe I can apply this also here for the enumeration of alternating sign matrices. And his idea is that he wants to prove that the number of alternating sign matrices is equal to the number, that is n by n alternating sign matrices, is equal to the number of totally symmetric self-complementary plane partitions of a 2n by 2n by 2n and so on hexagon, because George Andrews had already proved the formula for these plane partitions. So he could rely on that. And so his strategy is, he finds a constant term expression for the number of n by n alternating sign matrices. Then he finds a constant term expression for the number of totally symmetric self-complementary plane partitions of size 2n. As it turns out, these expressions are not the same. So what he does then is a trick that he had applied earlier, namely these are expressions in several variables, in x1, say up to xn. And what he does is he symmetrizes both expressions. Okay, then we get something else. And after a bit of manipulation, it turns out that after symmetrization, these expressions become the same. So this is his strategy. This is not easy to carry out, and as we have seen, it takes 73 pages. But it is still very interesting. And what I should add at this point is that Zeilberger, in fact, proves a generalization for which this is still the only proof. So the paper of Zeilberger appeared in 1996, and in the same year, Fred Kuperberg came up with a completely different proof of the alternating sign matrix conjecture, which involves the observation that the alternating sign matrices are in bijection with configurations in a model from statistical physics, namely the six-vertex model. So what is the six-vertex model? So here's a quick definition or page which has all the information. So here's an alternating sign matrix. Then on top, there is, if you wish, a translation from the entries of the alternating sign matrix into vertex configurations. So the graphs that we will consider would be these square graphs with open ends on all four sides. And all edges will have directions, will have arrows. And the possibility is that each vertex that you can have is two arrows in, 2 arrows out. And then if you think for a moment, okay, then I have 6 possibilities, which are the ones on top. And therefore the name six-vertex model. And the translation is that this particular configuration corresponds to F1 in the alternating sign matrix. This particular configuration corresponds to a -1, and the other possibilities correspond to zeros. And it's not very difficult to see that by doing this translation, you really get a bijection between alternating sign matrices and configurations with domain wall boundary condition, as the physicist said, namely from the sides, all arrows are pointing in, and on top and in the bottom, the arrows point outside. But inside, you can have whatever you want, so that the rules of the game are satisfied. And then to each of the vertices, depending on the local configuration, you assign a weight. There are many possibilities to parameterize this. I chose here the parameterization that Kuperberg chose in his paper. So for each of the possible vertex configurations, you use a certain weight, and then you, if you want to know the weight of a complete configuration, you multiply all the vertex weights. So these are n-squared weights. You multiply all of them, but I have to give you one more explanation, which is that you think that horizontal lines correspond to the variables xi, and vertical lines correspond to the variables yi. And then if you look at the particular vertex in this grid, then you will have an xi that corresponds to the horizontal line. And then you will have a yj, which corresponds to the vertical line. And the rule is that vertex will be labeled by the difference of the two, so xi minus yj. And with this labeling, then you compute this weight. So the x here is the x minus y from the next page. Yeah, right. And now define what the physicists call the partition function. The sum over all possible six-vertex configurations of this domain or boundary square weight of the configuration. We get a very complicated expression. So I abbreviate this long thing by this set n, x, and y. And then one shows a few lemmas, nailing down properties of this partition function. The first property is that this partition function is symmetric in the xi's, and it is symmetric in the yj's. The proof is extremely elegant by an application of the star triangle relation. I will show it here because time is running out. The second lemma allows a recursive approach, namely use a certain specialization, xi is equal to yj plus 1, and then it's not very difficult to see that this partition function collapses. So the ith horizontal line and the jth vertical line, more or less, they collapse. And you can express your partition function at this special value in terms of a smaller partition function where you remove these variables. Yeah, sorry. Yeah. That's right. And this is very easy to see that this partition function is a polynomial. We include the x0 because of symmetry, also includes the x1 and so on, of degree at most n minus 1. The important thing is that these three lemmas define something unique. Therefore, the only thing that you need now is a guess for what it could be. And then you only have to verify these three properties and you have an expression for the partition function. And this is what Isagin did in 1987, based on these equations that are due to correctly. Namely, he wrote down a completely explicit expression for the partition function. There's a certain product of things times a determinant, and the determinant has relatively simple entries. And now the only task is to specialize your weights so that each configuration has the same weight. And it turns out that x is equal to 1/2 and yj is equal to 0. This is such a choice that works, such that every weight is the same. The only problem with that choice is, if you look into the determinantal formula, that you will have zeros in the denominator. And therefore, you have to deform your choice in this way here, and with the goal that in the end you send epsilon to 0. And indeed, with this now deformed choice, you can evaluate the determinant explicitly by means of the Cauchy determinant formula. And therefore now you have a product where everything is explicit. Now you can do the limit epsilon to 0 safely, and you get the desired result. So this is Kuperberg's proof. But at this point, the question was whether one could only prove the original alternating sign matrix conjecture, or whether one could prove other things, say, for the symmetry classes of alternating sign matrices as well. And it turned out that these ideas can also be used to prove other conjectures on symmetry classes of alternating sign matrices. And this was inspired by a paper of Pinchilla, who gave a partition function for U-turn 6-vertex configurations. And Kuperberg picked up that idea. And in this, I would say, famous paper from 2002, he proved three of the conjectures by finding determinantal or Pfaffian expressions for partition functions, which are defined in similar ways, corresponding to alternating sign matrices in these symmetry classes. And then again, by specialization and determinants or Pfaffian evaluations, you prove the formulas. And from that point on, slowly things got moving forward. 2006, Krattenthaler proved the formula for class 7. The same year, Rasimov and Stroganov proved the even cases of what Kupperberg had missed. And the last remaining formula, the most difficult one, diagonally and antidiagonally symmetric alternating sign matrices, that was settled by Behrendt, Fischer, and Konradinka several years after that. Relatively recent. But so now the time is almost up. I have maybe more things prepared, but of course I cannot tell them. But what I do want to say is, so far we have seen a constant term identities approach to enumerate alternating sign matrices. That involved a lot of guessing. Then this 6-vertex model approach, also that one involves guessing, but it might be a bit easier. In 2006, Ilse Fischer developed a third approach, namely in terms of an operator formula for monotone triangles. The monotone triangles I should briefly define. It's relatively simple. What you do is that you take an alternating sign matrix, you keep the last row, and next you put the sum of the two last rows. Then in the third row from the bottom, you put the sum of the three last rows and so on. Then you get a matrix of ones, and then you report the position of the ones. The position of one in the last row is 4. The position of the ones in the next to last row is 3, 5. And then you get such a triangle, which is called monotone triangle. The property is that along rows, matrices are strictly increasing, along columns, matrices are weakly increasing, and then also in diagonal direction, matrices are increasing. For the alternating sign matrix, the first row must be 1, 2, 3, 4, 5 up to 1. But you may also put anything there. So here's the definition of monotone triangle again. So say you put K1, K2 up to Kn in the first row, some increasing sequence. Then Ilse Fischer found a very interesting formula, an operator formula. It takes, let's say, a few seconds to grasp the meaning of the formula, because what the assertion says is that K1, K2 up to Kn, these are certain numbers, but in the formulas, for the moment, they are kept as variables. You take this polynomial, this product, or INJ, which is a polynomial in Ki and Kj, and then you apply this operator, which contains these e's. These are shift operators. E x shifts x by +1. And so this is what the formula does. And in the end, so what you will get is a polynomial in the ki's and kj's. And in the final step, you substitute the actual values. This is a very interesting formula. And Lise Fischer used it to give a new proof of the alternating sign matrix theorem, of the refined alternating sign matrix theorem, and of many more things. And found new refinements. Right. So then I would have alternating sign traces. I will not do them. They are again counted by the same formula. Then, of course, the question of bijection turns up in 4 objects that are enumerated by the same formula. Where's the bijection? For Lise Fischer and Marta Pommelinke, they did find an algorithmic bijection between alternating sign matrices and descending plane partitions. So it involves the idea of the evolution principle, and therefore we are not sure whether this is a good bijection, but it's already remarkable to find even such a bijection. Refinements. I'm not going to this, and then I have an own conjecture, which is somehow hidden in the literature. And on my website, so it's a conjecture between 2 objects that Gog and Magog trapezoids that have been named so by Goran Zellweger, with 1 parameter less. It was already a conjecture by Ms. Lawrence and Ramsey, but I don't have the time to present it here. And therefore, I will change to my last page. Last page. Thank you very much.